In this session, we are going to discuss about Euler's method, a numerical solution of differential equations. Now, even if we can solve some differential equations algebraically, the solution may quite complicated and so are not very useful. In such case, a numerical approach gives us a good approximate solutions. So, a general initial value problem. So, we are trying to solve problems that are present in the following way. That is a differential equation of the form dy by dx equal to some function of x and y. So, any function which is of the form any differential equation, first order differential equation, y dash is equal to a function of x and y with some initial conditions y of a equal to some function, some value y of a is equal to a constant, where f of x y is a function of x and y of a is equal to some constant. So these are some examples of initial value problems. Examples: y dash equal to 6 minus 2 y by x with initial condition, another example initial condition, another example initial condition. Now how it works: the result of this formula is the value for y one h step to the right of the current value. That is y naught, y of 0 equal to y of x naught is equal to y naught, and y1 is equal to, we will let y1 is equal to y naught plus h into f of x naught y naught, where y1 is the next estimated solution value, y naught is the current value, h is the interval between each steps. F of x naught y naught is the value of the derivative at the straight point x naught y naught. Next value, so first one y of 0, then y of 0, then y1, which is approximately equal to y naught plus h into f of x naught y naught, then y2 is equal to y1 plus approximately equal to y1 plus h into f of x1 y1. Again y2 is the next estimated solution of y1 is the current value, h is the interval between each steps, x1 is equal to x naught plus h, f of x1 y1 is the value of the derivative at the current point, at the point x1 y1. Now continue this process, we will get y3, y4, y5, etc. So these are some approximated solutions. Now let's do an example exercise problem. The following question cannot be solved using algebraic technique by learnt earlier in this chapter, or this differential equation y dash is equal to sine x plus y minus e raised to x. It's very difficult to find the solution by using the algebraic techniques, so we can make use of Euler's method to solve the ordinary differential equation or approximated solutions. So y dash is equal to sine x plus y minus e raised to x, y of 0 equal to 4. So initial value problem with initial condition y of x naught equal to y naught, where x naught is equal to 0 and the function value at x is equal to 0 equal to 4, given that h is equal to 0.1. Now make use of Euler's theorem to solve the differential equations. Now first step, you know that y dash is equal to sine x plus y minus e raised to x sine x naught. Now first one, x naught is equal to 0, so we'll replace x with x naught, that is 0, plus function value at x naught, that is y naught, minus e raised to x naught. X naught is equal to 0, e raised to 0, so which is equal to minus 1.75680, etc. So that's an approximate value, that is function value. We'll call it as y1. Okay, note derivative dy by dx. Then we'll make use of Euler's equation to find y1. y1 is equal to y naught plus h, function value y of x plus h, x naught plus h, function value at x naught plus h. Now make use of Euler's theorem. Y of x plus h is approximately equal to y of x plus h into f of x plus y. So where f of x plus y is equal to y dash, since we have considered y dash is equal to f of x y, y dash is equal to f of x y is the initial value problem. So y dash derivative y dash is equal to function f of x y. So here f of x y is equal to sine x plus y minus e raised to x. Now y of 0.1, y of x naught plus h, y of 0 plus h is equal to 0.1. So y of 0.1 equal to approximately equal to y of 0, that is 4, y of 0 4 plus h into h is equal to 0.1, h into function value f of x y, or derivative of dy by dx at x naught y naught, which is equal to minus 1.7568, etc. So which is equal to, you can make use of calculator to find the answer, which is equal to 3.8243, etc. That is the first approximation, y1. So we know that y0 is equal to 0, then the first approximation y1 is equal to 3.8243, etc. First approximation. So the same process will continue till get the approximated solutions. Now second step, again doing the same process. Dy by dx is equal to sine x plus y minus e raised to x sine x. So instead of x we replace x1. x1 is equal to 0.1 plus y1. So here this is x1 and this is y1 to get the approximated value of y at x0 plus 2h, or y2 is approximately equal to, for finding the value of y2, x1 will choose x1 and y1. Now sine x plus y minus e raised to 0.1, which is equal to function value, which is equal to minus 1.8103 using calculator. then y2 is equal to y2 is equal to y2 is equal to y1 plus h into f at x1 y1. Just replace those values. Y1 equal to, so we have already calculated the previous step, function value at x0 y0, that is y1 is equal to 3.8243 etc plus h into h 0.1 into function value f of x1 y1, that is f of x1 y1 is equal to minus 1.8103, which is approximately equal to 3.643281 etc. That is the second approximation, y2. Similarly, we can find y3, then y4, y5, y6, y7, y7, y8, y9 and y10. y10 is equal to y of is equal to x0 plus 9h. x0 plus h is equal to x1, x0 plus 2h is equal to x2 and so on. x0 plus 9h equal to y10, function value at 10th approximation of the equation. Now after doing all those approximation, we will get the answer as 1.951974 etc. This is the approximated solutions to the initial value problem. Now let's look another example. Y dash is equal to, consider the initial value problem, y dash equal to y minus x, y of 0 equal to minus, y of 0 equal to 1 by 2. So f of xy is equal to y minus x, and x0 is equal to 0, y0 is equal to 1 by 2. Now given that in this problem, so use Euler's theorem with h is equal to 0.1 and h is equal to 0.5 to obtain the approximation to y1. So we have to find the function value at 1, y1, using Euler's method with h is equal to 0.1 and 0.05. Given that the exact solution is given, compare the error in the two approximation to y1. So if we replace x is equal to 1 or we'll substitute x is equal to 1, we will get the exact solution y1, function value at x is equal to 1. And by using Euler's method, we can have we'll get the approximated solution at y equal to 1. So first we have to find the approximated solution using h is equal to, with h is equal to 0.1, then 0.05. Since it's an approximation, definitely there will be some error, and we have to calculate the error in the approximations, in these two approximations, using h is equal to 0.1 and 0.05. Now given f of x is equal to f of x xy is equal to y minus x, x naught is equal to 0, y naught is equal to 0 point, y naught equal to 1 by 2. Now let h is equal to 0.1. First one, h is equal to 0.1, yn plus 1, yn plus 1 is equal to yn plus h into f of x and yn, or yn plus 1, nth one is equal to the previous function value yn plus h into f of x and yn, or plus h into yn plus h into derivative of dy by dx, derivative dy by dx. Now first one, y1 is equal to y naught plus h into 0.1 into f of xy is equal to, here f of xy is equal to y minus x, that is first one y1 is equal to x y naught minus x naught, which is equal to y naught is equal to 0.5 plus h into 0.5 minus x naught is equal to 0, which is equal to 0.55. That is the first approximation, y1. Then the second approximation, y2 is equal to y1 plus h into y1 minus x1, which is equal to 0.55 plus 0.1 minus y1 is equal to 0.55 minus 0.1, that is x1, which is equal to 0.595. Now continue in this manner. We will generate the approximation list, so given in the table. So this is the function value y1, y2, y3, y4, y5, y6, y7, y8, y9 and y10. So y10, which is equal to y of x naught plus 9h, that is y of x naught is equal to 0 plus first one y1 plus y2, y3 etc. 10h, which is equal to 0.1 plus 0.1 plus up to 10 times, that is y of 1. So y of 1 is equal to 7.7033129, and using the exact solution, using the exact value, function value, substituting x is equal to 1, that is y1 is equal to 1 plus 1 minus e raised to 1 by 2, which is equal to 0.640859, and the error in this approximation is equal to, or absolute error in this approximation is equal to y1 exact solution minus approximated solution, which is equal to 0.062270. Now similarly, using when h is equal to 0.05, Euler's method, yn is equal to yn plus 1 is equal to yn plus 0.05, that is h into derivative f dash or dy by dx or f of xy, that is yn minus xn, which is equal to now y1, first one y1 y naught plus 0.05 into y naught minus x1, which is x naught, y naught minus x naught, which is equal to y naught equal to function value at x is equal to 0 plus h into y naught minus x naught. X naught is equal to 0, and the function value at x is equal to 0 is equal to 1 by 2. Now y1 is equal to y naught plus h into y naught is equal to 1 by 2, that is h into y naught minus x naught, which is equal to y naught is equal to 1 by 2 plus h, that is 0.505 into y naught, that is 1 by 2 minus 0, which is equal to some value. And y2 again similarly, y2 is equal to y1 plus y2 is equal to y1 plus y2 is equal to y1 plus h into y1 minus x1, and which is equal to first approximation, x naught is equal to 0.1, we will get the function value as 0.54875, and x at x is equal to 0.2, you will get the approximation as 0.592247, and so on. And the last one, 20th approximation, we will get y of 1, since h is equal to 0.05. So we need 20 steps to reach 1 from 0.05, from 0 to 1. So there are 20 steps, with each step value is equal to 0.05. Now after doing all those approximation, we'll get y 20th approximation function value 0.686525, and the exact solution by substituting the value into the exact solution, x is equal to 1, we'll get 0.640859, and the absolute error is equal to difference between these two function values, and which is equal to 0.0032492. So it's clear from these two examples that if the approximation is increases, the error decreases. Since the first case the error was 0.062, and second case the error is 0.032, so the error is minimum in this second case. That means as the step or the interval value is decreases, or the step in this Euler approximation increases, the solution or the error will decrease.